V571 Lyr, VSX and GCVS will tell you it's a 1.25-day eclipsing binary, and I'm going to tell you it's actually a triple system with some very weak evidence for possibly greater multiplicity. I don't know. Is it safe to press the button yet? There we go. Okay, you've already got the abstract, so okay. This started out as routine work to refine the period estimate of this binary that had been discovered by the ROTC survey. There was a group of us at the AVSO, an informal group that we called ourselves the EB team, that had done a few papers on this subject where we took stars that had been discovered by ROTC that had fairly imprecise periods, and we derived better periods and published them as an IBVS. So this one was proposed by Marv Baldwin, I believe, and I set out to work on it. But even after finding some eclipses and revising the period estimate, subsequent eclipses deviated from that ephemeris by more than the amount of error I was expecting. So I continued observing for 15 years. And what I found was the eclipses alternately came 9 minutes early and 9 minutes late with a 5-year periodicity. So that immediately suggests that it's a light time effect due to this close binary orbiting with a third star in what turns out to be an eccentric system. So what I've done in this paper is I fitted the eclipse O-C curve, derived a mass for the third body, and so on, and come up with some arguments about saying we do understand what the mass probably is and what type of stars that there are. Okay, when I joined AVSO in 2001, or 2000, GRBs were the hot topic, with the ROTC telescope having just caught the first optical counterpart of a gamma ray burst in 1999. And when the ROTC telescope, which was several Canon telephoto lenses in front of big CCDs, when it wasn't slewing to GRBs, it was shooting a big patch of the sky, and that ultimately became the NSVS catalog. So for the observing history, it starts out with ROTC, and I recently retrieved the points that are publicly available as part of the NSVS dataset and made this light curve. The ROTC survey paper lists the period as 0.63 days, not atypical. They mistook it for they reported half what the period really is because the two eclipses are almost identical. Gil Lubke, who's here today, who's one of my co-authors, he was, I think, the first of our observers to work on this, and he caught an ingress and an egress, and that allowed us to home in on the eclipses and start timing the eclipses. And as I mentioned earlier, subsequent observations showed that the eclipses kept deviating from what I expected, and they were more than the amount of error I was expecting based on some previous stars. So I think a key thing was having an understanding of my own error, but also there was some lucky timing. It was a point on the O-C curve when eclipse times were really changing rapidly, so that was a big factor. I was a new observer, so there was some uncertainty as to whether I was doing heliocentric corrections properly and so on. So Arnie observed it at Flagstaff in 2001, and his data point was consistent with what I was seeing. So, as I mentioned, I observed it for another 15 years. Light curve, I made this way back in 2001 because the main point of this talk is not light curves, it's going to be O-C diagrams. The only thing I want to say is the two eclipses are nearly identical. Haven't modeled the light curve yet, but we will assume that it's two nearly identical stars at 90 degrees inclination, and these are both total eclipses. Out of eclipse, the magnitude is about 11.4, and the eclipse depth is 0.55 to 0.58 in V. Okay, O-C diagrams. I'm going to review what they are because in my experience, often there's a few people that aren't really comfortable with them, even though I know we started this talk with O-C diagrams from Dr. Smith. These figures are from a review paper about O-C diagrams by Christian Sturken in 2005 in the PASP or ASP conference proceedings. And he starts out with a very unusual O-C diagram, which underscores the fact that O-C diagrams are a very general concept, that you can apply them to almost any problem. always forget to breathe when I'm using a microphone. So this upper graph, which was his first figure in his review paper on O-C diagrams, is actually a graph of how much the declination of Uranus deviated from a model over the period 1650 to 1850. So what he did was he had observations of the declination of Uranus and a model of what they should be that I guess did not include Neptune. And so he plotted the observed minus his computed or modeled values, and he gets this clearly non-flat curve. If your model is correct, the O-C should be 0, and all the data points would lie along the center of the graph. So that just underscores that this is a general concept. An example that's much more similar to what I'll be doing is a graph of the observed times of minima of B.W. Vulpeculi in 1982. So this is Julian date. This is 80 days here, plotted against the cycle number of the variable star. And it looks like that straight line is a fantastic fit. But the problem is, what at really fine detail is it really such a good fit? So if instead of plotting just the JD versus cycle number, you subtract that linear fit from your data, and you're looking now at the residuals of the fit, and you have a much more sensitive analysis of your data. So that's what he shows over here. The center data set, which lies along the 0 line of this graph, uses exact slope for that straight line, or for the modeled times of minima. The other lines, the total error across the 80 days is 0.015 days. But this graph is so sensitive that you can see an error of 0.015 days across this graph, but you certainly can't here across a span of 80 days. So again, the point is, by taking your observations and subtracting the model that you believe is true, you then have a really sensitive analysis of whether your model is correct. So this is the data that I'm using in my analysis. This is an O-C diagram of the eclipse times for V571 Lyr. So what I've done is, for each eclipse that I observed, I computed a modeled eclipse time, and it's the sum of some epoch, the time of one eclipse that occurred in the past, plus the number of cycles that have gone by since then, multiplied by the period. So I just take my observation and subtract that computed time, and that's what I'm plotting here. If my model of a purely linear ephemeris, that is, the eclipses occur absolutely like clockwork, perfectly regular, if that was true, then all the data points would lie on the horizontal. But I think it's quite obvious it's not. They don't lie on the horizontal, and there's definitely some structure here. Now, because we've just listened to talks for several days about pulsators, I want to say one thing. This is not a light curve. Because I have had people look at my O-C diagram, and I tell them it's an O-C diagram, and they think it's a light curve, and it's not. This is just a deviation of the times of eclipses from being perfectly regular. Okay, now that I've beaten that horse completely to death, I just want to talk a little bit about the data points. Open circles are my observations. Circles filled with green are published observations. This black point here is Arnie's all-night run on the 1 meter at Flagstaff, which is consistent with the rest of the data. Yellow points, which don't distinguish so well from green up here, those are times of minima I determined from the SuperWASP archive data set. So publicly available data, but my measurements of the time of minima. And finally, the red points are ones I've rejected. The first two here were determined from the ROTC data, which just wasn't suitable for high precision timing of an eclipse. So that's fair enough. That type of data just isn't suitable for that. There's 3 red points here which were published, and I've rejected those because 2 of them are discrepant, and I found a website where that observer had published his light curves and shown the data that he used to derive the times of minima, and I would not have used those light curves to determine a time of minima. The data was quite poor, so I've rejected those data points. So now what are we going to do with this data? How am I doing for time? Okay. Cartoon to describe the system. Of course, we just see a single point of light in the sky, and what I'm claiming is that single point of light is embodying the light from two stars in a close binary, which I'll sometimes call the 1-2 pair. These are orbiting in a 1 1/4 day period. And what I'm saying is, in fact, that close pair is in an orbit that's a 5-year orbit around the center of a mass of a system that includes a third star that's also in orbit around that center of mass. But when I observe eclipses on one night, what I'm observing, what I'm observing on one night is the eclipses of this close pair. And this light, of course, is added in, but it's the eclipses of this pair that's making the dip in the light curve. So here we are with the stars at maximum separation, and for an observer on Earth who's down in the basement somewhere, these stars right now are presently at their maximum distance from Earth, so that the light that dips to make the eclipse takes a little longer to reach us. Perhaps 6 months later, that the close pair has moved in its orbit. It's now a little bit closer to Earth, and 2.5 years after the first slide, that 1-2 pair is near its closest point to Earth. The third star is actually furthest away, but we're not observing its position in any direct way. So the difference in distance over that 2.5 years, or half an orbit, this difference in distance, if you divide that distance by the speed of light, you'll get a time, the light time, which is the peak-to-peak excursion of the O-C curve. So back to this same old graph. When the stars are furthest away, the close pair is furthest away, and here we are on the O-C curve. Eclipses are coming in late because the stars are further away, and then they move towards us. Eclipses come in early because they're closer, and so on. Okay, back in '73, there's an interesting paper that reviews previous papers that have claimed to find third body systems, and basically says, hey, there's a lot of false positives going on here. People are claiming third body systems, and then a few more observations come in and they clearly contradict the story. So they came up with some criteria to apply to be more sure that you're really dealing with a third body system and not just some scattered noise. So, and I'm calling this paper FCH, so I don't have to figure out how to pronounce them. But their criteria start out by saying that O-C curve must match the physics of a real orbit of a third body system. And they recommended using Irwin's 1952 equation for that. Next, the secondary eclipses, well, if the primary eclipses are coming in early, then the secondary eclipses have to come in early, and vice versa. And the reason for this criteria is if you could have just a true binary, not a third body system, but if that binary was eccentric, you could have apsidal precession of the orbit, and then the primary eclipses could come in early and then come in late, and so on. But if that was what was happening, when the primaries are coming in early, the secondaries would be coming in late. So the primaries and secondaries. And finally, the fourth criteria is if you have spectroscopic radial velocity data, that data, which is physically related to, it is physically related to your O-C eclipse times. I don't think this is working. And so in that case, the radial velocity data and the O-C times must be compatible with each other. Okay, applying Irwin's equation. Looks a bit messy, but fortunately with tools like R available today, you don't have to get your hands really dirty building the mechanics to solve this thing. You can't be brains off, you have to make sure it really is converging and everything, but tools that are available make it quite easy to solve systems like this. So what do we have? The dependent variable over on the left is tau, and that's the O-C time. The dependent variable is our observation date, and that's embodied in V, which is actually the true anomaly, an angular measure of the position of that close binary pair as they move around their orbit. So time is embedded in V along with some of the other parameters. Then we also have E, the eccentricity of the orbit, omega, the orientation of it in the horizontal plane, A, which is the semi-major axis, the size of the orbit, and sine I, which is how much the orbital plane is tipped with respect to a line from Earth to the star. So we need to solve for those three parameters plus the period of the short pair, the closed pair, and the period of the third body orbit. And when we do that, and then plot the fit against the observed O minus C times, we get quite a good fit. So that satisfies FCH's criteria number one. We can fit this curve with Irwin's equation. Criteria number two, thank you, Ellen. Criteria number two is that primary and secondary eclipse times should track, the O minus C times should track. Well, I've now filled in the circles that represent the secondary eclipse. And, sorry, I keep hitting the wrong button. You can see that this curve fits both primaries and secondaries equally well. So we've satisfied that criteria. One note that I'll come back to later, the rug plot down here at the bottom shows which points I've actually used in making the fit. And I've chosen to tell the system to observe, to ignore these points in the middle when making the fit. So we'll come back to that. So the resulting system parameters, a very good estimate for the close orbit time. This uncertainty is 5 milliseconds. Third body orbit is 5.04 years, quite eccentric, which is reflected in the fact that that O minus C curve is not a sinusoid. If it was a circular orbit, that would be a sinusoid. But when it gets eccentric, it gets to have an irregular shape. And a semi-major axis, assuming the system, the third body orbit is edge on to us, semi-major axis of 1.3 AU. Okay, what more can we get? Well, we can keep going. Mass function is it's an equation or an analysis technique that dates from mostly using radial velocity data to study eclipsing binaries. And it's actually related to the O minus C time because time, the O minus C time, you divide by the speed of light and you get changes in the distance of the closed pair. If you differentiate that with respect to time, it's now radial velocity of the closed pair. So that O minus C curve really does encapsulate radial velocity information. However, it would be really noisy to derive it from that. And also, Mayer has transformed that equation to use O minus C time extrema instead of radial velocity extrema. So that's the equation I'll actually use. So everything on the right-hand circle is derived from my observed eclipse times and by the process of fitting Irwin's equation. On the left-hand side, this is just the masses of the stars in the system. So if I could solve for M1 and M2 or pull them out of the air magically, then the only unknown would be M3, and I've now solved for the mass of the third body. So let's keep going. My co-author, Russ Robb at the University of Victoria, obtained a spectrum of this system back in 2007 using the 72-inch at DAO, and his interpretation of this spectrum is that it looks like an F7 dwarf plus or minus 2, and he sees no evidence of a third body. So clearly we have to return to the no evidence of a third body question. But let's run with the F7. Arnie, besides doing that time series, also did a 3-night calibration of the field back in 2001, and he got a B minus V of 0.48, and he's checked that against APAS data, and it supports that number. So when I take Arnie's color and plug it into Allen's tables of color versus spectral type and so on, it comes back as F6 or F7. So that's a nice agreement with Russ's spectrum. It does suggest that there's no reddening of this field, and I thanked Dave Turner yesterday for concurring that that's reasonable for this kind of position and distance. So I now have a mass for the M1 plus M2 pair. I'm claiming it's two stars that are about F7, each with about 1 1/4 solar mass. So M1 plus M2 is about 2.5. Okay, plugging all these things into those equations that I showed you earlier and doing some hand waving to come up with the size of the error bar, it looks like the third star has a mass of 1 solar mass plus or minus about 1/10. Well, if you had a star of that mass is going to have a spectrum kind of similar to the spectra of the 2 stars in the closed binary, which are F7. That's going to be about a magnitude fainter. So that kind of fits with Russ not seeing the third star in the spectrum. Similarly, our photometry sees constant light from that third star. So what's that going to do to our light curve? Well, if we just had 2 equal stars, 90 degrees inclination, then when they go into eclipse, the flux would go down to 50%. But in fact, it goes down only to 59%. So do a little bit of arithmetic. That third star must be 41% as bright as each of the 2 stars in the close pair. So about 1 mag fainter. And that, again, is compatible with the kind of mass that we're talking about for this system. So how are we doing against FCH's checklist? Well, yeah, we can fit it with that equation. Secondaries and primaries are doing the same thing. And we've come up with a reasonable mass for the third body, which doesn't break our light curve, third light properties, and kind of matches the spectrum we have. So I think this is a reasonable solution. And the O-C times versus radial velocity criteria, well, we can't do that because we don't have spectroscopic radial velocities. Okay, 2 minutes to go. Okay, so I think I have an answer. So now let's go back and criticize the data some more. An O-C curve is actually a plot of residuals. Well, now let's take the residuals of those and take my O-C points, those open circles, and now subtract the fitted third body lifetime effect curve from Irwin's equation. And the little black dots in the middle are now my residuals of how much my observations misfit that fitted third body curve. Well, the residuals aren't random and stationary. Early on, they have more scatter. Well, I was a newbie. My flaps weren't terribly good. Some of the software I was using for time of minimum determination back then is known to give problems, and I'm not yet sure that I removed all those bad points. And also, I was using short observing runs, sometimes as little as 3/4 of an hour on either side of the minimum. I now know better. I like at least 2 hours on either side. So I had greater scatter back here. More recently, yeah, I'm using longer runs, larger aperture, better flats, darker sight, and my scatter is less. Now, what's really interesting is in what I'm calling cycle 3, around 2008, 2009. And the observed O-Cs are all below the fitted curve. And you see that here in the residuals, which are about 1 standard deviation below the mean. The green dashed lines represent the standard deviation of the residuals. Oh, okay. Okay, so I can breathe? Good, thanks. This relates to why I chose not to fit cycle 3. I did an earlier fit, including all the data, and even using all the data, the observations on cycle 3 kind of came in lower than the fitted curve. So I said, there's something here trying to tell me a message. So let's just omit those and let whatever negative residuals are trying to be there, let them really have a chance to stand up and shout. So I just fit cycles 1, 2, and 4. And that gives me a clearer view of the fact that the O-C times are coming in lower than the fit in cycle 3. And then when I fit a smooth curve through all my residuals, that's this skinny black line through here. It, of course, shows that dip. So what might that be? Well, it could be just statistical fluctuation. You can take a perfectly fair die and throw it 10 times and come up with 1 every time. That's valid statistics. It could also be weak evidence of a fourth body in the system, perhaps low mass and or high inclination. and a long period of at least 15 years. So I plan to keep observing the star. Okay, so further work, notwithstanding cycle 3 coming in a little low, the scatter in the times of minima are still greater than the Qui-van Woerden algorithm or other algorithms which tell you is your error, which worries me. And that problem is not unique to my observations, but it's something that merits further study. I'm continuing to try to rework this data and track down errors, but I think the fact is the scatter is greater than what we understand it should be. Those residuals in cycle 3, I haven't actually tried to fit a fourth body to it. I'll have to make heroic assumptions to fit anything. Of course, there's different approaches I could take. I chose to ignore the cycle 3 data. Instead, I could have ignored the cycle 4 data, in which case cycles 1, 2, and 3 would fit perfectly, and cycle 4 observations would lie above the fitted curve, and that would suggest something else. So what I've done is quite subjective, but there is something going on in this data set, I think, that needs further observation. Spectroscopy, now that we think we know what that third star looks like, can we possibly detect it, and how much radial velocity shifting of the lines should there be as these stars go through their orbits? That needs to be looked at. And of course, I should be doing multicolor observing and Wilson-Diviney style modeling of this system. For people who want to do this kind of observing and analysis, there's lots of stars to work on. I'm quite fond of a list that I call, the Otero Plus stars, because they're a list of more than 1,000 stars that are posted on the EV section website that are all based on publications by Sebastian Otero as lead author and many of his co-authors about 10 years ago. Many of those stars have not had any observations made of them at all. So who knows what's out there? There could be some, well, there's almost certain to be some interesting stars in there. And of course, there will be other lists. Something else you can do is look at online O-C diagrams for stars that do have some observations. For example, this is the O-C diagram at the Czech O-C gateway site for V571 Lyr. And I've outlined here where my pointer is, that's an O-C of 0.01 days, and this is minus 0.01 days. And that's a very large O-C for a star that's just supposed to have a linear ephemeris. So if you see an O-C diagram like this, it tells you either the star is doing something really interesting, or you've got some bad data there, and so good data is needed anyway. In the case of this O-C diagram, the answer is both. These are the 3 discrepant points, or 2 of them are discrepant. These are 3 points that I rejected. But this O-C diagram, if you saw something like that, this would be a good star to observe. Okay, acknowledgements. I sort of got into this based on something that had already been launched by Mark Baldwin and other people of the eclipsing binary enthusiasts here at the ADSO. And I remember way back when, 2000 or 2001, Dan Kaiser and Gary Walker and other people being quite welcoming to me as a total newbie. So they're to blame for all of this. And the SuperWASP data archive, which I've used, I rely heavily on all kinds of software that's in the public domain. Well, that's not the correct word. That's free and open source. Public domain would be something else. And not only for this star, but for all my eclipsing binary observing, VSX and the Czech Society's O-C gateway site are really invaluable. References, we can talk more about that later if anybody wants to. Otherwise, I welcome any questions either now or later. Thank you.